One of the very important steps in analytical chemistry is method validation. Method validation is the process of proving that an analytical method is acceptable for its intended purpose. If you read any analytical paper that is talking about a certain or a new analytical method for a certain chemical or a certain analyte, you will always find a section that is called method validation. In method validation, there are a number of parameters that has to be guarded, and they have to be measured, and in order to validate our method and to say that this method is actually acceptable for its intended purpose. Uh, for the section which is the method validation, you will always find that they are talking about certain parameter, especially the specificity, linearity, range, limit of detection, limit of quantitation, and robustness. So let's talk about these one by one to understand what exactly do they mean and why they are important. So first of all, the specificity. Specificity is the ability to distinguish the analyte from anything else. It's very important that your analytical method is specific and it's able to distinguish the analyte from all the other chemicals or all the other things that may interfere with your analysis. So it must be selective and it must be specific. Linearity is the linearity is how your calibration curve is linear, and usually when you do your calibration curve, so you have certain points and then you do the method of least square and then you draw your calibration curve, which should be a straight line. And normally not all the data point will fall on the in the line. Some of them will be above or below. So it's but this is the method of least square. And usually when you do that using the any software, you will find that there is the R squared value. The R squared is the square of the correlation coefficient of your for your calibration curve. The the this the if the value of R squared should be as close as possible to 1. 1 means that all the data points actually fall on the line, the straight line, but it's never 1 because there is always a random error. So it always will be 0.9. It should be 999, something like that. So the closest it is to 1 means that there is a good linearity for your calibration curve. Then the precision, and the precision will include instrument precision. So it's very important to measure the instrument precision when you repeat the experiment several times, whether the instrument will give you similar results or not. Intra-assay precision, intermediate precision, and most generally the inter-laboratory precision when you give the same sample to different laboratory and you try to see if the results are similar or not. What is the precision if we run the same experiment under the same condition in different laboratory? So precision is very important. Range is the concentration interval over which linearity, accuracy, and precision are acceptable. So there's something called range, and because not all the concentration of your sample will actually have the um, good linearity, good accuracy, and good precision. But there is usually a range of concentration for your sample. And it's very important that the intended use of your method, um, the range of the concentration that all the values of linearity, accuracy, and precision are acceptable are the ones that are intended for that particular method. For example, if you are measuring the concentration of, let's say, for example, copper concentration of water, of drinking water, and you are using a certain method to measure the concentration of copper in drinking water. Normally, you would expect that the concentration of copper in drinking water would be a very small concentration in the nanomolar range. If you use a certain method and the expected value of the concentration of copper in water is not in the range, then this method cannot be used for the measurement for that intended purpose or for measurement of copper in drinking water. So this is what we mean by range and why the range is important. Detection limit is another very important parameter that we need to measure for our method and calculate for our method. Detection limit is the lowest detectable concentration of your sample or of your analyte using this particular method. So each method we use has a different detection limit. So how can we measure the detection limit? Detection limit means that the concentration, the lowest concentration, or the smallest quantity of the analyte, which is significantly different from the blank, because the blank usually doesn't give you a zero value; it gives you some value. Like when you done the experiment in the lab, and usually we have the blank, and then we calibrate the our device with the blank, the spectrophotometer, when we did the spectrophotometric determination of copper. So you calibrate your device with the blank, but actually if you don't calibrate it, you will find that your blank will have some value. So we need to know what is the smallest quantity of our analyte that is significantly different from the blank. How can we measure the detection limit? The detection limit is different based on the method we are using and based on the instrument we are using. So first of all, we need to measure the signal that we get from N replicate samples. So we have an N replicate of sample containing the exact same amount of the sample, exact same amount of the substance, not different concentration, the same concentration, and we measure the signal from this sample. And let's say that the signals is called Y, so this is Y sample. And then we need to compute the standard deviation of these measurements. So S, which is the standard deviation, is the standard deviation of our samples. So first of all, we see what is the signal from the sample. This is the average, okay? So the average signal from the N replicate of the sample is Y sample, and the standard deviation will be S sample. Then we measure the signal from N replicate of the blank. So you have several replicates of the blank, which contains no analyte, of course, and you find the value of the signal you get from the blank, which is called Y blank. This is again the average of all our measurement of the blank, so it's Y blank. The minimum detectable signal can be defined as the minimum detectable signal. It's called YDL equals Y blank plus 3S. So the minimum detectable signal is basically 3 times more than 3 standard deviation more than the blank signal. So it's the blank signal plus 3S, which is the standard deviation, 3 times the standard deviation. Now, if you have your sample, when you measure your sample, you have the signal that you get from the sample, but you need to correct it because now you know that your blank has a certain signal. So the corrected signal of the sample will equal the Y sample, which is the average of the measurement of the N replicate of the sample, minus the Y blank, which is the average of the signal of the blank. We know that for the calibration curve, usually the corrected signal, not the sample signal, but the corrected signal is proportional to the sample concentration. That means that the corrected signal, which is Y sample minus Y blank, will equal M, which is the slope of our calibration curve, times the sample concentration. So the corrected signal equals m times the sample concentration. So now we need to measure the minimum detectable concentration or the detection limit. If we replace the Y sample here with YDL, then the sample concentration will be the minimum detectable concentration or will be the detection limit. So it's very important to understand that if you replace the sample concentration with the minimum detectable concentration, you will end up with the sample concentration to be the detection limit. So when you do this, Y sample here with YDL, we know that YDL equal, so YDL equal Y Planck plus 3S. So it's going to be Y Planck plus 3s minus y Planck will equal m times the minimum detectable concentration or detection limit. Okay, y Planck will go with y Planck, and then we will see that the 3s will equal m times detection limit, or we can say that detection limit equals 3s over m. So detection limit will equal 3 the standard deviation divided by the slope of our calibration curve. So detection limit is usually 3 times greater than the noise, which is the random variation or the random error that we usually find in any measurement, the noise in the Planck. Um, so limit detection, the detection limit is 3s over m. So it's 3 times more greater than the noise. There is something also called lower limit of detection or LOQ. The lower limit of detection is 10 times the standard deviation over the slope. So it's very important to distinguish between the detection limit and lower limit of detection. If you see again any analytical paper that has a certain analytical method, you will find that they have to report what is the detection limit of their method and what is the lower limit of quantitation of their method as well. The lower limit of quantitation will be 10 times standard deviation over the slope, while the detection limit is only 3 times standard deviation over the slope. Reporting limit is another important thing, which is the concentration below which regulation said that the analyte is reported to be not present, even if you observe that there is some signal. So there must be some limit for reporting. If you see this is the minimum concentration depending on your method that you can say that the analyte is present. If we after we do our calculation, if we find that below the reporting limit, we find the concentration is below the reporting limit, then we say that the analyte was not detected. Robustness of any method is the ability of an analytical method to be unaffected by small changing in operating parameters. So even small change in operating parameters will not affect the results that you get. So it's very important that your method is robust. Otherwise, it's very difficult to depend on this method or to be reliable. So let's have an example to see how can we calculate the detection limit. So if you have from previous measurements of a low concentration of analyte, the signal detection limit was estimated to be in the lower nanoampere range. Signals from 7 replicates of the sample was with a concentration about 3 times the detection limit were the following ones. The reagent blank, so these are the values of the sample, the signal from the sample. And then the reagent blank give these values. So these are the values of these are the one of the y of the blank, the average of these, and these are the y of the detection limit. The slope of the calibration curve for higher concentration is 0.229. So the question now, so we have the slope, we have the values of the lower detecting the sample values, and we have the value of the Planck, the values of the signal of the Planck. So we need to find the signal detection limit and the minimum detectable concentration. So these values are for the sample. So the first thing we need to do is to find the average of the signal of the Planck. So now the average of Planck is very important. Average of Planck, of the signal of the Planck, which is dy Planck. We will find that if we calculate the average, you will find the average of the Planck is 1.26 nanoampere. And then we need for the sample to calculate the standard deviation. So we need to calculate S, which is the standard deviation of the sample. So you need first to calculate the average, and then you start calculating the standard deviation, and you find that the standard deviation is 0.56 nanoampere. Of course, when we report the final results, then we should say that the average is 1.3 and the standard deviation is 0.6. Okay, but we will leave this because the significant figure here, we should have only one significant figure for the standard deviation, and the last significant figure of the standard deviation will be the last significant figure of our value. So we should, in the final results, we should report it at so, but because we still need to do extra calculation, we're going to leave it with in this way. Now we know that the signal detection limit, we can calculate the signal detection limit, YDL will equal Y Planck plus 3S. So it will equal 1.26 plus 3 times 0.56. So the minimum detection, the signal detection limit is 2.94 nanometer. So this is the signal detection. So this is the lower detection limit for our signal, or the signal lower detection limit. And then the minimum detectable concentration here, the detection limit will equal, as we said, 3S over M. So 3S over M will be 0.56 divided by M, which is 0.229. That will equal 7.3 micromolar. So the detection limit for this method is 7.3 micromolar. This is the detection limit. Now the second part of the concentration of the question is asking you what is the concentration of the analyte in a sample that gave a signal of 7 nanoampere. So we know now that the Y of the sample minus Y Planck will equal M time concentration. That means that the concentration, if we rearrange the equation, will equal Y sample minus Y Planck divided by M, which is the slope. So the Y sample is 7 nanoampere minus the Y of the Planck, which is the average of the Planck, it's 1.26 nanoampere, divided by the slope, which is 0.299 nanoampere over micromolar. So the answer here is going to be 25.1 micromolar. So this is the concentration of the sample that give a signal of 7 nanoampere. So remember that we need always to account for the value of the blank, because we did not calibrate the device first. We have a signal from the blank. So you have always to use the corrected signal. You cannot use the signal straight away. You have to correct it. You have to see the value of the signal from the sample and take away the value of the signal that is from the blank in order to calculate what is your